Okay, so we have that super awesome geometry formula. What's the geometry formula? Area of the circle. That's just it? The volume is the area of the circle? Oh, times the height.
Good morning, North Stars. Please rise for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Have a great day, North Stars.
Awesome. Okay, so.
Yeah, why did we do that twice?
What? You would
There's an echo.
Oh, really?
Yeah. It is.
Really?
Yeah, talk a little louder.
A little louder?
Yeah.
Echo?
Yeah.
Cool. Some physics happening there, I'm sure of it. Okay, so area of the circle.
No, what is that? It's something.
I think it's the speakers.
It's maybe.
Projector from the recording.
Okay, so here's a circle. So what if I stand over here? Better?
No.
Awesome.
Speaker turned down the volume of the speaker.
Turn on the volume of that speaker?
Yeah.
Not sure I can. What if
The remote.
What if I do that? Is that better?
Yeah.
That's better?
You.
Okay. So what do we call this in geometry?
Circle.
Okay, yeah. On that three-dimensional shape, what did we call the circle here and the circle here? The bases, right? The bases were those two flat shapes that were identical on a cylinder or a prism. And so we had the area of that circle, which typically we call big B, so that we could use the equation for anything, right? And then times the height. And so this cylinder is kind of on its side, so it can roll nicely. Okay, so the height here is going to be, so this is big B, so the height here is going to be the height of the cylinder. Okay, and then what is the area of the circle? How do you find the area of the circle? Right, pi r squared. Okay, so go ahead, in terms of pi, that means you don't need a calculator, okay, because we're going to leave pi in the answer. In terms of pi, find the volume of that cylinder.
36.
Okay, Tyler says 36 pi, right? The radius is 3, we're going to square that, and the height is 4. Quite sure why I don't put in the, there we go. So we have, we have 36 pi units. Can you see them? They're harder to see on the display.
Inches.
Yeah. I'm not sure how easy they are to see on the PDF. Okay, so 36 pi inches cubed. We leave a lot of things in terms of pi. We just leave it like that. We know that means 36 times 3.14. So we're talking somewhere just over 100, right? Cubic inches. So how can we get that cylinder in calculus? How can we generate a cylinder?
Integrate.
Integration, okay, how did you know it was integration?
Because I looked down.
Okay, because you looked down
And then
in the notes. Okay, super. We're doing integrating, so that's always a safe bet, right? Okay, so if we picture the center of the cylinder here, as an x-axis, how could we then generate this solid?
as a disc.
How could we make it in calculus? Okay, that's really what we're going to talk about today. Is how do we make that solid? Okay, So the kind of cool thing is, as we make this solid, we're going to start to see really these geometric formulas show up in the calculus. Okay, and so actually I think I'm going to rearrange this. What did I just do? I just did something that I didn't want to do. There we go. So if we talk about, I guess I don't want to rearrange it. I'm going to stick with this page next. If we talk about finding the volume of a solid, what we do is we take, in this case, that surface, that round surface ends up just being a straight line. And if we take that straight line and spin it around the x-axis, we can sweep out a circular surface. So what does that look like when we do something like that? The function for a straight line is what sort of function for just a horizontal line? Yeah, x equals a number. If we let the outside surface of the cylinder we just calculated the volume for, if we let that outside surface be the function, how much is our function? If we go right down the center with an axis, how far is that outside surface away from the axis? Look at your picture on your first page. We let the axis go right down the center of that cylinder. How far is the outside surface from that axis?
4 inches. 2 inches.
3 inches, right? We go right down the center of the cylinder. We take a line and we draw it right down the center of the cylinder. Okay? And that outer surface is 3 inches away from that axis, the center of the cylinder. So if I just type in a 3 here, okay? And I think I have to hit tab. There we go. If I just type in a 3 here, now I have that outside surface. I don't think I can control it through the smart board. I have to control it through my computer. Then I have that function, just like we had it. There's that outside surface of that cylinder. And if I take that function, and if you notice, we have kind of 3D capability here. So what I've done is I've given you a perspective now where it's kind of like you're drawing on a dry erase board on your table, right? Pretend that dry erase board is a grid, and you had your x and your y axis sitting on the table. You draw your function of y equals 3, and now we're going to pop out of the surface of your table and sweep that function across above your table and below your table. Okay, so we're going to sweep that function. And if you look up here, I can actually create that 3D capability. We're going to sweep that function and we're going to create, so there we are above the surface of the table, and now we're going below the surface of the table. And we can go ahead and create that cylinder. So we've just rotated that function, and if we look at that, we can see that we have a cylinder. And in this case, since I'm just sweeping out a surface, I have to change my program a little bit to actually sweep out a solid. pretend that that cylinder is actually totally solid, that you don't see a hole through it. We've actually swept out a complete solid. Okay, I have to change my program a little bit. But now we have this solid cylinder. And we've created it by sweeping out that base here and that base here just by taking that function around the x-axis. So to accomplish that using calculus, we take this function and we sweep it around just like I did. We can create this three-dimensional surface. So really what we're doing is we're taking what we, and this is something we definitely have to be capable of doing here, is we take this, what we call incremental rectangle, and we pivot that rectangle about the axis. And once we pivot that rectangle about the axis, we have this kind of skinny disc. And that skinny disc is nothing more than a real skinny cylinder. So it's kind of like a Riemann sum. If we add up all the discs from 0 to 4, we're going to get that entire cylinder. And so if we take a look at this, do you see the equation for the area of the base here? Okay, so here's your area of your base, there's your pi r squared. Here is your area of your base times your height. Notice your dx is this incremental skinny disk, but if we add up all the dx's from 0 to 4, we end up with the height of our rectangle. So if we go from 0 to 4, then all of these dx's end up being accumulating to 4. So what is this radius here, mathematically speaking? The height of that radius is how much? The length of that radius is how much? 3, which ends up being your function, your f of x. So we can accomplish finding the volume of this using calculus just by integrating that, just by accumulating the volume of these disks. And so this whole expression right here is the volume of that disk. And then we can add up all those disks, which is what your integration is going to do. So let's take a look at this then using calculus. So what's my function here? Using calculus, your function is what? How much is your function?
3.
Function is 3. Alex, can you get our iPad and click on? Oh, you are. Good. Awesome. My nose. Okay, your function is 3. And where are we accumulating our disks from? From what starting point to what ending point? 0 to 4. So 0 to 4, and then we have a pi here. Our function is 3. So we're integrating that base area, and we're stacking that up from 0 to 4. And so we're really integrating what? What are we integrating here? Yeah, I mean, what is this numerically? How much is this? It is 9 pi. Dx. So how do we integrate that? 9 pi is nothing more than what? A constant. So what can we do with it, right? Because 9 is a constant, represents the radius squared. Pi is a constant. What can we do with a constant when we integrate? Yeah, bring it outside. So really, what are we integrating here? When you integrate 1 dx, what do you get? X, right? This is when you're integrating dx, it's like 1x to the 0 power, right? If you have a 0 power, you bump it up, you end up with a new power of 1 divided by 1. So you end up with 9 pi x from 0 to 4. So if we take a look at that, compare it to your geometry, your 9 pi is your what? Pi r squared, right? Pi times 3 squared. Your x is going to be how much? It's going to be 4, right? Because we're going to come here to evaluate it, and we're going to say, well, I have to put a 4 in here, and I have to subtract a 0, right? Upper bound minus lower bound. So this is going to end up being your, what was 4 for this whole shape? It's going to end up being your height. And so we end up with, through the integration process, we end up with that geometric formula for volume of a cylinder as we evaluate that, that integral. So we end up with our 36 pi cubic inches. Now, if you remember geometry and you have a nice geometric shape like this, and you want to use geometry, go ahead and use geometry. College Board will not dock you any points if you use geometry. Most often the case, though, is that we're not going to have a function that's going to give us a nice geometric formula. So what sort of functions would give us geometric formula? Functions that lead to geometry. Okay, functions that would lead to a geometric shape. Right. Okay, if we have a linear function that passes through 0, like y equals what? Y equals x? Or y equals 2x, or y equals a half x. And we rotate that, and the way we show that on paper is we just put a little circle, like a little circle with an arrow. We rotate that about the x-axis. We sweep that out. What shape is that going to give us? It's going to give us a three-dimensional shape. If we rotate this, that means we're coming out of the board and then going back into the board. Yeah, that's going to give us a cone. So if you're having a hard time visualizing it, that's where this comes in handy. And I've got the website for this for you in just a second. If I just type in y equals x, okay, so we look at this. There's the equation y equals x, okay, and so picture that coming out. So really what we have here is we have that rectangle. If I would draw that rectangle in here, that rectangle starts out with the 0 height. Yeah. And then it grows to a height of 4. And we spin that rectangle. We're going to get discs that are really big on this end and really tiny at the origin. And so if we stack up discs that are big, smaller, 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 we're going to get something that looks like a cone. And so if we spin this, we can see, and let me zoom out just a little bit so that it doesn't cut off the bottom. There we go. So if we spin this, we can see we've got that cone shape. Anybody remember the volume of a cone? Yeah, it's just the volume of the cylinder divided by 3. that has the same radius and same height. So it's just pi r squared height divided by 3. That's going to give us our cone. So it's those two things, the linear and the constant. And sometimes they do give you a linear function. You know, that constant one is the one we just did. That when we rotate those about an axis, we can get nice geometric shapes. Okay, so if you're dealing with those functions and you want to do the geometry, awesome. Keep doing the geometry. Really, what happens though is, since this works for constant and linear functions, it also works for any other function you can think of. So I'm going to just go ahead and rotate the square root of x about the horizontal axis. So now we're talking about these disc shapes. As we rotate those around the axis, we're going to end up making this what do you want to call it? Maybe a bell-shaped sort of shape. So if we change this function to the square root of x, which would be x to the half power. So there's your x to the half power. And we can see kind of what that looks like. And I can just put it into a three-dimensional spin. Slow down the spin a little bit. There we go. So here's that three-dimensional, you don't want to really call it a cone because it doesn't have straight sides, but it's more of like a dome shape. So we have that, oops, didn't want to zoom in. Let me zoom back out here. There we go. So we have that cone-shaped, and we got that cone shape by just sweeping around that square root of x around that axis. So just a quick break here. If you want to scan that QR code, that'll take you to the applet file that I made that will allow you to do a three-dimensional rendering of your functions, which will come in handy when you're doing homework, just to get an idea of what this function looks like when you rotate it. So that being the case, how are we going to calculate the volume of this shape? Okay, so take a second using this formula. Which now looks hopefully a lot like area of the base times the height. Okay, it's just that our profile is going to change based on our function. Go ahead and calculate the area of, or excuse me, I said it wrong, the volume of this three-dimensional shape. If you want to do the three-dimensional rendering, you can actually scan each other's QR codes. Or let me get that totally on the screen, so if you want to, you can scan that too. So we are, what is this function?
It's square root of x.
It is. So we are putting in, we are integrating x to the 1/2 power. So be careful. This is not a straight side. This is not a flat surface. This is a domed surface. Okay? So we are integrating that function. what shape am I creating when I spin that rectangle around the axis? And if you're unsure as to what shape you're creating, look at the end, the blunt end of that. What does this look like when we look at it end on? What is the shape of that base, in other words? So we look at that end on. Here it is coming around. All right, there's the top of it. There's the side of it.
It is a bell.
And there's the front of it. Okay, when we look at that straight on, it's probably the easiest way to do it. What shape is that?
Circle.
Circle. So that's your area function. What's the equation for a circle? Pi r squared. Where are we measuring our radius from? Nope. Where's the radius? The radius goes from the axis of rotation up to the function. Okay, that's what we're spinning around.
Oh,
Okay, so here's the radius. Ladies, little calculus, please. Thank you. Okay, here's the radius from the axis of rotation up to the function. So we know that this is pi r squared. It's always going to be pi r squared. We're always going to make a circle here. But what is my radius? How much is it? Well, right here it's 1. How much is the radius here? How much is the radius here? 2. The radius is following what pattern? The value of what? Value of the square root of x. Okay? So that radius then is what? Square root of x. What do we need to do to the radius? We need to square it. Once we square the square root of x, what do we get?
X.
Good. That's not bad to integrate, right? I hope. Please, maybe? What are my limits of integration? Let me get that out of there. Okay, I'm going to start at the tip of my dome and go all the way out to that flat surface of my dome. What do you get for your volume? So the nice thing is that whenever we spin something around an axis, no matter what axis it is, it could be an X, it could be a Y, it actually won't be a Y. We'll just do x-axis or horizontal. We don't do vertical axis. It could be the axis itself, it could be a line parallel to that, up above or below. We're always going to sweep out something that is circular in shape. So the nice thing is we're always going to be integrating pi r squared, always. It's just that what is the radius? It's going to have to relate to that function. Then we get an answer for 5?
8 pi.
Like that? Is that far enough? Okay, so I got pi x squared over 2 from 0 to 4. And plug 4 in there, and Tyler says that's 8 pi. That sounds believable. Yeah, I think I still have, I will just go with inches cubed. I'm not sure I put units on this one. Yeah, units cubed if there's nothing there. Okay, so if you've gone into the file, the applets that allows you to do the 3D rendering, they actually give you the answer too. But this is definitely one you should be able to do without a calculator in terms of integrating this. and finding a numerical answer. If I just switch back to the applet here, we can see the answer here is 25.13. Okay, that is 8 times 5. Okay. So tonight's homework is going to be spinning things around this x-axis. Okay? A few things you need to be able to do. You need to be able to sketch the function. You need to be able to sketch that rectangle and identify the radius. Okay? So this picture right here, I'll doctor it up just a little tiny bit. I'll say radius equals square root of x. Everything you see in this picture, you should be able to produce on a test question. Okay? Getting me a sample rectangle, maybe even really impressing the grader by putting a dx there, because the width of your rectangle is dx, and we're going to add them all up from 0 to 4. Okay, that represents the accumulation, right? The differential. So reproducing a sketch like this is something that is, again, part of that setup now as we talk about 3D shapes. They don't expect you to draw something 3D. Okay? I'm going to just, is it okay to, actually you have that information. I'll keep that down here. All right. You've got some time to work on WebAssign. A lot of us are really far behind. Please get caught up today. Okay? Please. All the tutorials for 7.1 and 7.2 are out there. Please get caught up today so that you're a happy camper a week from today. We like happy campers.